Thank you so much. It's a real pleasure to be here. I think it's my third time at the IPAM, and I enjoy it a lot. And I want to thank the organizers for setting up this extremely nice event. So about the three jobs, actually, I mean, job number one is where I do my research, job number two is where I do my teaching, and job number three is where I go on vacation, maybe once. I was planning to present a status report of some work that we have been undertaking since around 2018 with a variety of collaborators. So Linnea Grant-Samuelson, who is now at Microsoft Station Q, Ron Goram-Nives-Vivat, who is transiting from Beijing to Abu Dhabi, Sylvain Ribaud, who is at affiliation number 3 in Saclay, as well as Universality, and Paul Roux, my thesis student with Sylvain. Okay, so this was basically supposed to be the tale of two loop models, but I want to focus very soon on the second one of those. So there are two loop models in 2 dimensions that look very similar, but which differ in the details. So one thing is the Q-state Potts model. So this model you can define in any dimension. You have spins that take Q states, and the interactions have some symmetric group permutation symmetry. And as we saw this morning, it's equivalent to a loop model on the medial lattice via the Baxter-Cullen-Wu construction. And as a loop model, it has actually a UN symmetry, which is something that is not often discussed, and I won't discuss it here. And it's related, since I need to relate things to vertex models, this is related to the integrable 6-vertex model and the temporally Lieb algebra. Now, what I want to do here is to look at models defined in the full plane. So if I were to, for example, define it on a cylinder with circumference L and look at this in a transfer matrix formalism, the boundary conditions would have to be periodic. So if I were in any dimension, I could say that SQ commute with the partition algebra. And the partition algebra, once I descend to 2 dimensions and require sort of planarity up to periodic boundary conditions, it becomes the Potts temporally Lieb algebra, some version of an affine temporally Lieb algebra with a weight square root of Q per loop. So this is not what I'm going to talk about, but I could have talked about it because everything that has been worked out for the ON model has also been worked out for this Potts model, but I need to focus a bit. So the ON model in the beginning, it's a model of vector spins living in sort of an n-dimensional sphere, and they have an ON symmetry, as the name says. And after some suitable modification, which was, for example, promoted by Bernard Nienhaus in '82, it becomes a loop model. And this loop model now is also related to a vertex model, which is an integrable 19-vertex model. And it also has an algebraic underpinning, something that is often called the dilute temporally Lieb algebra, but it can also be called the Motzkin algebra. Those two guys are actually isomorphic. So here is, of course, a small typo. This should have been ON. So ON commutes with a diagrammatic algebra that's called the Brouwer algebra. And in 2 dimensions, that descends to something that we call the unoriented Jones temporally Lieb algebra. And this I will explain better in a while, but this is just to have some overview. So here is the ON model. So the best lattice you can work on maybe is the hexagonal lattice. And on that hexagonal lattice, you draw closed contours. Well, the other one doesn't look like it's closed, but it's because I show only a small part of an infinite lattice. And each loop has a weight n. And in addition, there are some local vertex weights, which can be 1 if a vertex is empty, and k if it's occupied by a small piece of loop that comes. And now what I want to do is to consider this model where the partition function is the sum over all configurations of loops that you can make out of those 4 vertices. such that I get the n to the power number of loops and k to the power number of monomers, and a monomer here is one blue step on the lattice. And of course, the reason that these configurations here have only weight k is because that there's a handshake between edges, so that you have to share your edge with the other vertex. And if I wanted to build up everything, I could locally act with a transfer matrix of this type. So it locally builds up 8 configurations, and then it will proceed in imaginary time. Good. Now, let's look again at this partition function. So there are two special values of the monomorphic fugacity. So if k starts, say, by being 0, there is nothing in the model. And if I increase k, there's some particular value, kc, which is the smallest one of these two values here, where one loop becomes of size infinity. And when you go across this value, then you are renormalization group attracted to the other higher value of k. And for any finite value of k larger than this first k, then you flow to the second k. So you have two phases of this model. One phase where loops are dilute, that's the small value of k, and one where they are dense, that's the large value of k. So this model is extremely nice. It contains a lot of special cases. For example, in the dense phase, for n equals 1, it's side percolation, side meaning these hexagonal faces that we have seen a lot of times, including in Hugo's talks. If n is 1 and dilute, it's an Ising model, so the loops are then just contours between plus and minus spins in a critical Ising model on a triangular lattice. If n tends to 0 and we are dilute, we have self-avoiding walks, or close to self-avoiding walks maybe. And if we take either of them because they coincide and n is 2, we have a Gaussian free field, or the so-called XY model. And I'm actually going to talk about none of these models, although my model contains them all. And this is because I will shy away from any particular value of n, because I know that when n takes a particular value, these tend to be logarithmic conformal field theories. And so correlation functions will both contain power laws and logarithms, and this is something that just today I don't want to do. So on the next slide, you will see what precise condition I'm imposing on n. And the objective is to try now to understand correlation functions in the case of a generic value of n. Now, we can go on to the next slide. So this model has a certain central charge, which is conveniently parameterized by a parameter beta. This is maybe not your favorite parameterization of the central charge. There exist maybe 3 or 4 different reasonable ways of parameterizing it. And what I want to do is to take the real part of beta squared positive, and then in particular I want beta squared not to be a rational number, because if it were, then I might run into these logarithmic CFTs. And I also see a question. I will just remember this, okay? So this will be answered, but a little later. Yes?
Beta not real in general? Why are you taking the real part of this real? It can be a complex number.
Yeah, sure. I mean, the conformal field theory makes sense by analytic continuation to complex values.
And there's also beta is in terms of n.
N is minus 2 cosine pi beta squared. And that should have been on that slide, but somehow it wasn't. Okay, and now we are going to talk a bit about conformal field theory. So usually people write this cat table parameterization of critical exponents or conformal weights. And this I also have maybe a non-standard way of writing, but it's very reasonable. So I define something that I call a momentum. It depends on these labels R and S, which are those that many of you, well, most of you, all of you know. And the conformal weight is then the difference between this momentum squared for R and S and for the ground state, which is 1, 1. And now the first thing that I want to claim is that this model contains 3 kinds of fields, which I will generically label by these labels R and S. So there is something that, some fields which are degenerate, and the fields that I shall need are those with R equals to 1 and S equal to an odd positive integer. For pods it would have been any positive integer, but for ON it's an odd positive integer. These fields have left and right moving conformal dimensions the same, so they are diagonal. And they are degenerate because there is a singular vector sitting at level S. Now, there's another type of field in which I just take these left and right dimensions here, and P, if you are willing to work in the complex continuation of this theory, P could be anything. And I'll soon show you what they are good for. And then there's a third type of field, which are non-diagonal. I don't have the same left and right moving dimensions. And then there are these strange constraints here. R is half a non-negative integer, and S is an integer divided by R. So already now, this is very weird, right? Because usually, if you learn about CFT, you learn about minimal models, and you know that R and S are integers living in some restricted range. And then maybe if you go on a little bit, then you know that there are some kind of extended minimal models, as they are often called, in which there is not this restriction that R and S belong to a finite range. But now what is really maybe different here from what you might have thought about before is that sometimes these guys are not integer, and actually S in particular can, as a fraction, it could have any denominator that you want. Now, what are those good for?
Yes, can I ask, so why do you shift by the P11 squared in all of these formulas?
So this is just, I mean, if you haven't seen this parameterization before, it looks strange, but it's really the same thing as this R times P plus 1 minus SP squared minus 1 over 4P P plus 1. If beta squared is 1 over P plus 1. It's the same formula, it's just written in some way that I have now gotten used to, and maybe you will. Good. Other questions? Then I'll change. Okay, so the interpretation of these fields within the loop model are as follows. So these diagonal fields here, they are such that if I insert such a field, the loops that turn around that point are going to get their weight modified. So you already saw this was our generic loop weight n. And by inserting such an operator, I can get another weight to the loops that turn around this point, which depends on P in a particular way. We don't need to write it down.
And the word diagonal refers to the fact that the two scaling operators, scaling dimensions are the same?
Exactly. Left and right have the same scaling dimension. And the other one, VRS, that is to say the VRS without this diagonal index, but this one, the non-diagonal one, that's the one that Coulomb gas has done so much to describe. It inserts a number of lines, namely 2 times R. So this partially explains why R had to be in this writing half an integer, because then the number of lines here is actually going to be a non-negative integer. And also, if those lines were to wind around their insertion point, then they would pick up some phases that are related to the S parameter. So some complex phases. And now the last type of operator, the one that was degenerate, well, that's all operators of energy type, and the most relevant one is V13, and I will just call it the energy operator. And if you define the model as a lattice model, you could also wonder when would it actually converge to a CFT. So we have already seen that there had to be a condition in general on n here. But actually, you just need this V13 to be irrelevant, which gives another condition here. So the CFT exists when the real part of beta squared was positive, and here you need this real part to be larger than 1. Okay. Now, I have a dream, and I will present you this dream. So here is a Riemann surface, which is very complicated. For example, it has 2 holes, but it could have many holes. And on top of that Riemann surface, I have inserted various kinds of operators, VRS, with black dots. And out of these points come a certain number of loop strands that connect in a certain way. Some of them, they turn around non-trivial directions. Some of them turn around other insertion points. But none of them just form a small loop that turns around nothing, because this I don't want to have. And I insert these diagonal operators at the crosses. And now all these loops, they are going to have weights. Some of them have weight n because they are just contractible loops. Others are turning around an insertion point, so they have this modified weight. And the question is, can we compute these correlation functions? And the answer as of today is that certainly not. This is way too complicated. And I want to show you the first few steps on that road that will eventually, in some time, maybe, lead somebody to understand this problem more fully. So the open curves here, they define what I will call a combinatorial map on a Riemann surface. There will be a more precise definition soon. And there is also something called the Siegel axioms, of which a small part is that basically if you want to build up this generality, you need basically to understand 3 basic building blocks, which is an annulus with 1 operator insertion, a disk with 2 insertions, and a geometry where 2 circles somehow join to become a pair of pants. So there's no figure, you can just look at my pants if you want. And these blocks are glued together by sort of integrating over eigenstates in a certain way. And maybe a decent goal in this world would be to try to understand well these 3 things first. And also this I will only report on partially.
Jesper?
Yes.
Just to understand the conditions on the red loop, like some of them look contractible, is that allowed?
Yeah, so some of them are contractible, and then they will just have this weight n. So n is like the default weight that I can give to a loop. But then you could have other kinds of weights depending if a loop turns around some puncture. Okay, so the progress this far is that the fields are related to irreducible representations of the affine Temple-Lieb algebra. So I have to confess that I'm suffering from some kind of schizophrenia. Okay, so I work in the continuum limit and I work in the discrete, and I'm trying to see connections. So I believe strongly that what you can do on a lattice, you can push to the continuum limit, and what is interesting in the continuum limit, you should be able to do on a lattice. Okay, so I will just bluntly say things like this, that the fields are related to the E-reps of some algebra that lives on a lattice. And we have found a bijection between correlation functions and combinatorial maps. So this is why we should be interested in combinatorial maps. We have found that conformal symmetry is enhanced in a certain way because of the existence of this degenerate operator V13 to something that we call interchiral symmetry. I will come back to that as well. And we also believe we understand that the global ON symmetry of the model has some interesting interplay with conformal symmetry, so that really to understand this problem of correlation functions, you should pay attention to both of them. So now, dreams are very good, but you have to be realistic. So my first goal is to try to understand correlation functions for up to 4 points on the sphere. And to that, you will immediately notice that 2-point correlation functions you basically understand as soon as you can say what the critical exponents are. Okay, so for those operators that I have presented, these dimensions are known. That being said, there was a recent paper by Nolan, Shin-Sun, and others in which they understand a very new exponent that's called the backbone exponent, and which is not at all in this setup here. So somehow the game goes on, but let me not talk about that. In the end, I hope I will get to the end and show you that the case n equals to 3 with these operators here, we claim we conjecturally understand in all cases for all combinatorial maps. And for n equals 4, we have a partial understanding using also conformal bootstrap. And I wanted to now summarize this progress. Okay, so the first thing I wanted to mention very quickly is those diagrammatic algebras. I am here cheating a little bit because you remember well from the first picture when you saw those ON configurations that there's also empty space. Here I will just draw you diagrams that focus on the essential part, which is where the loops are going, disregarding that it should somehow be interspersed with some empty space. So in general, if I evolve something in imaginary time, I could imagine a very general algebra that's called a partition algebra that tells me how points on one time slice and on some other time slice are connected via partially constructed pieces of, say, FK clusters. And this would be generated by something that permutes two guys, something that disconnects one guy from the guy below it, and something that connects two neighbors. Okay, and this partition algebra is very big. There are papers about it in which a certain number of special cases are spelled out. And one thing that is particularly important for me is a very particular combination of the S's, which is called E. And it has the effect that two nearest neighbors are sort of contracted together on the bottom, and a new thing is opened on the top. And this is my way of dealing with loops. I scan over the loops. And when there's one loop that is somehow trying to end, then it gets this kind of cap. And then here's a new one that starts with a cup. And if I bring together all possible products of these EIs, I can now generate loops, actually all loops on a non-periodic strip. And if I want my strip to be periodic so that it's a cylinder, I have to add this periodic generator that contracts in the same way the first and the last side. And I also need a translation operator that we have also seen this morning. So things have been well prepared. And finally, I need something that looks a little bit unphysical maybe, which is for a given diagram that I could construct by making products of these E's and U's. I want to introduce some kind of translation operator that's not an honest-to-goodness translation, because the only thing it translates is how lines that connect the top to the bottom, they are called through lines, how they are connected among themselves. So the guy here that connected here is now going to connect over here instead, as you see, and so on cyclically.
I didn't get that.
So without shifting, okay, so you see on the top here, you see some arcs, and you see some starts of lines that will go to the bottom. okay? So those arcs you don't touch, but you touch how the top and bottom is glued together. So suppose I cut it with a knife here in the middle, and then I have to glue things 2 by 2 because loops don't intersect, and now I just shift this way of gluing, and this is called a pseudo-translation. And this I'm going to need. So now, this affine Timberley-Lieb algebra is infinite dimensional, and if you want to get something finite dimensional, you need to take quotients, because there are two things that can happen. You could have loops that run around your cylinder, so are non-contractible, and the algebra doesn't tell me what weight to give to them, so I just take a quotient and claim that they should also have weight n, the same as here. And then these through lines, they could keep spinning around the cylinder axis, and they could do so as many times as they wanted. And I want to impose the relation that once they have all spun around once, I want to unwind them and replace by a weight 1. And this is, gives me a quotient which is called the unoriented Jones-Timberley-Lieb algebra. And then if now you draw things like this, which is like a half diagram, you know, remember that I was cutting through my diagrams. So those half diagrams here, they are called link patterns. If I place below them, now time goes down, sorry about that, then I'm going to get another link pattern. So this is the set of these link patterns. They form a representation, a module. It's called a standard module on L spins. And it uses these two numbers, R and S. R, twice R is the number of lines. And S is a phase that corresponds to how those lines will spin around. And it's made in such a way that T is diagonalized on the standard module, and it has eigenvalue e to the I pi s. And since t to the 2r is 1, it requires s to be quantized. As always in quantum mechanics, you are quantized by the boundary conditions. And these labels R and S, now I claim they carry over to the CFT the way I have shown. Okay, something that was done a long time ago in 1987 by Philippe, Hubert-Saleur, Jean-Bernard Hubert, was to compute the conformal partition function on the torus of this model. So if I set small q equal to e to the 2 pi I tau, and tau is the module of the torus, they obtain an expression of this form here. So the partition function is the sum over S with the values we have seen times some characters, diagonal degenerate characters, which have this expression here in terms of this Dedekind eta function. Then you get a sum of R and a sum over S, exactly with the constraints that I already announced. And then there are going to be some multiplicities, L, and some characters that are non-diagonal and which have this expression here. Okay, now maybe, I'm sure that there's going to be another slide where I say it, but maybe I should now say something about n integer or non-integer, okay? Because now when I say multiplicities, you would think that multiplicities are maybe presumably positive integers, and they are not, because representations of On, you can make sense of them for any n, treating n just like a formal parameter, using a construction that's called the linear categories. So the idea is that you sort of just imagine first that n is an extremely large positive integer, and you see all the representations that you can get. And then you just claim that they will somehow analytically continue. And when you do so, some of the dimensions, or here they turn out a bit like multiplicities, they could become 0 or even negative, or if I take into complex numbers, they would become complex. And the message of the linear is that this does not matter. You are entitled to do this, so we'll do it. So here it is, this partition function, and we have a certain number of Virasoro representations that correspond to these characters, a diagonal level S-degenerate representation, an indecomposable representation with this character, and a Verma module with this character, and they fit in up here. And these multiplicities, there's a nice formula for them, which was partially obtained in the first paper, the one with the torus partition function. I mean, they basically explained how you could go around to compute it, but the nice formula here was only obtained by Rietzeler in 2001. And it's a pretty funny formula with a largest common divisor sitting here. So you know it exists. Well, this is what I already explained, right? So a formula like this, it looks like you have some kind of sure-while duality. Here you have objects that are defined in the CFT, and here you have some multiplicities, and the multiplicities that must be somehow the dimensions of the stuff that that the conformal symmetry commutes with in a certain sense. So what is really happening is that we have both conformal symmetry and we have ON symmetry. And the definition of the linear categories I already told you about. So E-reps of ON are just defined by Young tableaus. So here are some examples, including the empty one, which is the trivial representation. They have known dimensions. They have known tensor products. They are given by Newell-Littlewood numbers. And the loop model interpretation of all of this is that a loop simply carries this one box Young tableau. It's the fundamental or defining representation of ON, whereas empty space corresponds to the trivial representation. And then if you want more than one line, then you have to fuse together these ones here, like a tensor product, and then you have to find E-reps of this. So for example, if you want two lines, it could be that those two lines will just connect up and sort of disappear, or it could be that they persisted and then they could be symmetrized or anti-symmetrized. So this is like this Young tableau and this Young tableau and this Young tableau. And that makes sense for any n. So here's the formula again. So I claim the proper way to understand it is that the ON model, CFT, has a space of states. I call it a spectrum, in which on the right-hand side of this product here, you see our CFT representations. And on the left-hand side, we see some other, the representation of something else corresponding to ON, which is such that the multiplicities that you saw just before is just the dimension in ON of this lambda RS. And now, one important point is that from the torus partition function, you just get this multiplicity. You don't really get what this lambda RS is. You just get its dimension. So if you want to compute what it is, you need to do something a little bit different, which I will soon come back to. So if I introduce some kind of strange representation here, where on the first line of my Young diagram, I have T minus K boxes, and then below it I have one box, one box, one box. That's called an alternating hook representation because of this sign here. So this is not really a representation because you see it comes with minuses, so it's not a good representation. But it turns out that this lambda RS, which is a good E-rep and expands out over Young tableaus with only positive integer coefficients, it can be written in this way that looks very much like the other formula, except that now as an argument you should use this alternating hook representation. And when you take polynomials of it, you just you compute things by making tensor products. So this is a very neat formula that actually solves this problem. And there exists we have found another equivalent formula which makes it more clear that the expansion coefficient should be integers, which is not at all clear from this writing. But this first writing is the most simple to state. Yeah. Let's have a look. Let's have a look how it starts. So for example, if you take one line with trivial momentum, then as I said, it corresponds to this fundamental representation. If I take two lines with trivial momentum, it corresponds to this symmetrized Young tableau. If I take two lines again, but such that there's a minus sign each time the two lines are interchanged by winding around the periodic boundary condition, then I get this anti-symmetrized representation. But then it becomes more complicated, because when I move down in the list here, if I want 4 lines, for example, you see it expands out over 5 different EREPs of ON. Okay, so it's more complicated. There's not a one-to-one correspondence between these capital lambdas and the ON representations. So there are consequences of this for correlation functions. So, of course, 2-point correlation functions, they are just given by the conformal dimensions up to normalization of the field. If I want 3-point correlation functions, you know, all of you know, I think that their coordinate dependence in CFT is also just fixed by global conformal invariance, but there's a structure constant involved, and that structure constant is not automatically determined because I already normalized my fields on the level of 2-point functions. And what about 4-point functions? Well, if you look in the big yellow book of conformal field theory, you know that if there are degenerate fields, you can determine 4-point correlation functions by solving certain differential equations. Well, actually, that was in the BPZ paper, to be fair. And this could be done here as well if the theory had these diagonal fields both with a non-trivial S index and with a non-trivial R index. But this is not the case. And that's the whole point. Okay, this is why we cannot expect correlation functions to obey differential equations in this model, because we have only the fields, the degenerate fields of type 1s. We don't have the degenerate fields of type R1, because they were replaced, recall, by these non-diagonal fields that were used to insert loop strands. Therefore, if we want to solve this theory, unless somebody can figure out something completely different, we need to make the best use possible of the degenerate fields that we have. And then for the rest, we need to solve 4-point functions with a procedure that's called conformal bootstrap that I will explain in a while. We can do a little better for 2 reasons. So V13 generates a larger symmetry than conformal. That's called interchiral symmetry that we can take into account. And second, we can take also into account the global ON symmetry. So if you consider, for example, a 4-point function, you would expect it to expand out on objects G, which are called conformal blocks. Conformal blocks are, once you know the dimension and the central charge, they are given by a recursion relation due to Zamolodchikov. It's much debated, however, by probabilists if that expression converges, but I will not be concerned with such petty details. And the expansion coefficients here are what I will call 4-point structure constants. And now it turns out that there are certain shift equations that come from this V13 that will relate the DRS when S is shifted by 2 units. So that means that I can decide to lump together these conformal blocks into larger objects in which I use these known ratios. The ratios are given by gamma functions, product of gamma functions. And then I'm going to get a simpler problem in which my S variable is constrained to an interval of length 2. And so this I will call interchiral conformal blocks, and I will talk about interchiral symmetry. So now the question is, how do I determine these D coefficients, the 4-point structure constants, with S in this smaller range? And to do that, I'm going to claim that if I take 4 points, and if I bring them close together 2 by 2, the result shouldn't depend on in which order I bring them close together. So if I bring 1 and 2 close together and 3 and 4 close together, I have an expansion in terms of the exchanged field here, V. That's called the S-channel expansion, and then I can make a T-channel and a U-channel expansion. And I want all of these to give the same object, and that imposes enough constraints that one can actually solve, at least numerically, for the correlation function. So the situation is as follows. We know the spectrum, we know which fields exist in the theory, and we can constrain the solution space by fixing the ON symmetry of this exchanged field. And in favorable cases, this gives a unique numerical solution, or it could give a solution space of some dimension. And our conjecture is that each solution to these crossing equations gives us a valid correlation function in the ONCFT. And we have addressed this in a physicist kind of way by computing the first 30 correlation functions with R equals to 2, 3, and 4, all of them. So it looks like it works. Good. About this formula here, recall we have two ways to prove it. One is to compute the torus partition function in which one of the periodic directions is twisted by inserting a non-trivial group element of ON. That's going to produce this character, not just its dimension, and this is why we can get it. And the other one is an algebraic way, which I will skip because I fear running into some time issue. Okay, now correlation functions. So the claim was that correlation functions are in bijection with these combinatorial maps. So what is a combinatorial map? So a combinatorial map here on 4 points is a prescription for how many lines go out of each point. And each point comes with is considered up to cyclic permutation of the lines that go out of it. So you see the second drawing here, it's the same combinatorial map as the first one because, well, you see the points here, they go to the same points, they turn around each other in a different way. But the third one here is different because here the line that cyclically comes after the one that connects up to the top. Here, the next one in cyclic order connects to the right, whereas here it connects over here. So this is a different combinatorial map. And there's a definition also of what it means to be weakly connected, which basically amounts to saying that you cannot, you are weakly connected if you exploit the structure of the Riemann surface that you are living on. So for example, this guy is not weakly connected because if you want a handle on your torus, your combinatorial map has to turn around that handle. Otherwise it's not weakly connected. And we have results for the number of these maps and for the number of weakly connected maps. So I can tell you how many correlation functions there are. And in particular with 4 points on genus 0, the number of C maps is this. I will also need to know how this interacts with my conformal bootstrap. That is to say, I need somehow to figure out in each channel what is the minimal number of lines that will propagate. And to do that, I will draw some loop that separates the first 2 points from the last 2 points to get to the S channel, and then I will just count what is the minimal number of loop segments crossed by this red loop, and here that is 2, so the signature is 1 because I have this factor of 2 in my convention for counting loops. And this is something that's important for the bootstrap in order to compute a unique object whenever it's possible. You need to know these signatures. So here are some conjectures. So if you take any endpoint function of diagonal or non-diagonal fields, then the dimension of the space of solutions is given by these numbers of weakly connected maps. And the critical limit of a loop model correlation function is a solution of these conformal bootstrap equations. And In parallel, the set of correlation functions is a basis of solutions for the corresponding conformal bootstrap equations. Okay, I want to flash here to you a horrible function. This is called the Barnes double gamma function. You recall the central charge is given in terms of beta. Set q equals to this, so it's not the number of states in a Potts model, it's some other q. Define this terrible function by this terrible integral, as well as some shift equations, because when the integral doesn't converge, you need to get it into a region where it connects. If some of you know an upsilon function, it's related in this way. So just recall there's a terrible function like this, okay? It's called the Barnes double gamma function. Maybe you love this function, then I'll withdraw the word terrible. It's a fantastic function. Jan really likes this function. Okay, now let's get to 4-point functions. Okay, so the general setup is you have 4 points, and I want to consider the most general 4-point function that you can imagine. So if a loop turns around point number 1, it will get weight W1. If a loop turns around, if it separates points 1 and 2 from 3 and 4, it will get weight Ws, and so on and so forth. Of course, not all of these loops can exist in one given configuration, but if I sum of all configurations, it can be used to weigh anything, okay? So there are 8 different loop weights, this one and the other 7. And I want to consider correlation functions as a function of these 8 parameters. Now, in the lattice model, let's define then the correlation function for a cylinder of circumference big L in the S-channel expansion, where the distance between the 2 groups of points is small l time slices. For an ON model with monomorphic acidity K, loop weight N, all these other loop weights, what can we say about this correlation function? Well, let's see. The first thing I can say is this equation here. Okay, so I claim that such a correlation function, you can expand it out in ratios of the eigenvalues of the unoriented Jones-Temple-Lieb algebra that we have seen, divided by the maximum eigenvalue, and some amplitudes. This is not at all obvious that there should exist such an expansion. If you want to compute such such complicated 4-point correlation functions, you have a priori no reason to think that they should be expandable in terms of eigenvalues of a much simpler transfer matrix. But this I claim they can be. Second, suppose now I look at these amplitudes here, and I take the ratio of the amplitudes of some correlation function with some values of the W's with respect to another choice of the W's. Then I claim that this ratio of amplitudes here will precisely coincide with the corresponding ratio of 4-point structure constants in the conformal field theory. This is now outrageous claim, but it's true. Because here on the left-hand side, you see I have an L dependence. I'm in a lattice algebra, okay? So I claim that if my lattice is just big enough to accommodate the corresponding representation of a fine Temple-Lieb, then this ratio of amplitudes does not at all depend on L. Worse, or better, it doesn't depend on K. It doesn't even depend on the model being at its critical point. Okay, so these amplitudes here, they have nothing to do with conformal field theory, because they would be true even if my model was non-critical. Third, up here, of course, there are many, many eigenvalues sitting in the same representation of the Temple-Lieb algebra. With the same value of R and S, you could have 100 eigenvalues or 1,000. But there's nothing, no label here distinguishes the eigenvalues of each representation. So these ratios are constant on each representation. So it almost looks like a Wigner-Eckert theorem of quantum mechanics, but somehow lifted up to the affine Temple-Lieb algebra. So this we have studied in dozens and dozens of cases, and we have invariably found this to be true, but we don't know how to prove it yet.
Is this the right-hand side product of the insertion on the boundary, or is it not?
We are always in the bulk. Always in the bulk. Okay, now I'm at slide 27. Am I allowed to go to 30? Because my time is basically out. Is there a chairman around? Yes. Fine, thank you. Okay. Here is a schematic setup of 2- and 3-point correlation functions. You know that there's a coordinate dependence, and this coordinate dependence is fixed by global conformal invariant, so I won't write it down. But suppose I write here a constant on top of 2-point functions and another structure constant on top of 3-point functions. Then I want now to introduce something that's called a reference structure constant, the B's here for the 2-point functions, and the C's for the 3-point functions. And Jan is positively thrilled because he sees his Barnes double gamma function everywhere. Okay? Now, if these fields were diagonal, you should just take the R index to be 0 and the X index related to the corresponding momentum in this way. It was found some 10 years ago by Delfino and Vitti that if you want the probability that 3 points belong to the same FK cluster, or say to the same percolation cluster on the same FK cluster, it would be given precisely by this formula, Cref, evaluated on diagonal fields in such a way that the Wi weight for turning around those points would be 0. Okay, it was shown numerically 3 years later by Yacine Iklev, Universality, and me, that this extends to the case where Wi, the diagonal loop weights, are anything. So they are all given by this. Now, in 2 slides, you'll see that I'm going now to make a more general claim again. So suppose now I take my 4-point structure constants and I normalize them by multiplying the certain products of these reference structure constants. And what remains I call D. Then what we find is that these D's here, and that's another maybe outrageous claim that we don't know how to prove, but it seems to be true. This is just a polynomial in N. And if the X-channel expansion, X being S tier U, involves a diagonal field, then they are also polynomials in the modified loop weights. And finally, if there is some Wi, it's also a polynomial Wi. So these D's are just polynomials in anything, and polynomials, where can you get that? Well, that you can only get in the lattice algebra. So we need to understand this lattice algebra, because this will be the key to understanding 4-point functions. So we have, dozens of cases where we have computed these guys by conformal bootstrap, but we need to derive them using some diagrammatic algebra. And here is my last slide, okay? So we find very surprisingly, I think, that if you take a general 3-point function where at each point you insert a certain number of loop lines, so a combinatorial map, there's only one combinatorial map for each choice of R1, 2, 3, then we find that its 3-point structure constant, properly normalized, is just given by Cref. So in particular, if you take 3 points and you take each of the 3 points to spit out 2 lines, how could they connect if I'm not allowed to make self-contractions? Well, they can only connect in such a way here, okay? So it means that I'm asking what is the normalizing factor in the, what's the probability that 3 points sit on the same loop?
Why can't they be connected different?
Because the definition of these operators that spit out R-lines, two R-lines, is that they cannot self-contract like this. And this was also the definition for a
But you
combinatorial
still
map.
can connect them other way around with the planarity, right?
Yes, but it would be the same combinatorial map, okay? It looks topologically maybe different, but it's combinatorially the same thing, okay? So here, here is for this particular case, so R equals to 1, 1, 1. Here is a transfer matrix computation of this probability, this normalizing factor in the probability. And if I drew on top of it this Barnes double gamma function, it would just completely coincide. You couldn't even see the difference with the pink points.
Precisely is what are the axes?
And on the axis here, this is the loop weight. So the lower curve shows how you go in the dense phase of the ON model, and here you go into the dilute phase. And on the other axis, it's the value of this normalizing factor in the probability. Okay? And we are in tough competition with Shin-Sun and collaborators in Beijing. They have actually proved, using the conformal loop ensemble, they have proved this particular case, 1, 0, 1, 0, 1, 0, in unpublished work, okay? But our formula is addressing the general case. And I'm really sorry, I used too much time. Chairperson is very nice, so I have finished now. Thank you so much.
Thank you very much.